Okay, let's go ahead and look at these. Thanks again for wearing your mask. Appreciate that. And hopefully you used your Healthy Together app today. So the first one, this is going to be an oxidation of the benzylic position. So we're going to be dealing here with this benzylic position. Okay, so if there is a beta hydrogen on the benzylic position with sodium dichromate and acid or KMNO4 and acid, what we'll get is the carboxylic acid. So it cleaves everything past that first carbon and it oxidizes as fully as it can, which is the carboxylic acid. Okay. Questions about this one? What you're looking for in this one is one beta hydrogen. So it works for primary, secondary groups. It does not work for tertiary. In the second one, we have the wrong problem. So anybody that was confused, sorry. That problem, if you put no answer, would be perfectly correct because there was no answer to that one. Since it is a benzylic, I apologize. Okay, so again, we're looking at this position. NBS reacting with that gives us the bromide. So the first step here is we're going to do benzylic bromination. That selectively puts one bromine right there on that benzylic position. And then we have a base that does an E2 elimination to give us our final product. So the second one is this base that does an E2 elimination to give us the product. And we still have the benzene. Okay. Questions about that one? On the Chem 101 homework, there's been some issues with it, the drawing not working. I do apologize. I'll be adjusting that. I know who has been taking those problems. And whenever you see one, go ahead and send it to me. What I'll try and do on this next set of homework is if you see one where you believe the drawing is not working, send it to me. I'll check it. Once I verify it, I'll send it to the whole class so everybody in the class knows and you won't get as frustrated on that. I do apologize. This is a new homework system for me, and it looks like they're having some issues with a few of their drawing programs. As far as grades, I'll adjust for those. So whenever I find one wrong, just like on a test, everybody will get an adjustment. Yes, ma'am. Yeah, let me change that and see. I believe that's a setting, but I'll have to check. Okay. I don't do that on the quizzes and I don't do that on the exams until everybody's turned it in. Okay. All right. Any other questions? Yes, sir. Yes, ma'am. No, I'm actually gonna start it after class. And then some people are work after class, so I'm gonna leave it up until 10 o'clock. So you got a long period to take it. But once you start it, you only have 15 minutes unless you have an accommodation. If you do have an accommodation for time, please just send me a note before any quiz or exam to remind me, and I'll make sure that gets into Canvas. But it is not during class. The exam will be during class time. Quizzes are after class. Okay. Right. And again, the quizzes will be like the exams. There's going to be multiple questions, just like you've seen on the homework. That's one of the reasons I've done it on the homework. So kind of get used to you and your friends not having the same problems. So the quiz will have enough variation that you probably will not have the same. The exams will have enough variation where no two people will have the same exam, but the topics will all be the same. Yes, sir. I can't hear you. It'll cover through what we did today. Okay, so what we covered today will be on the quiz. Of course, probably a little bit more 16 and 17, but I'm not saying that anything from today is not counted. Anything from Thursday is not going to be on the quiz. Okay, yes. The quiz is probably about 5 to 10 questions in 15 minutes. So yeah, sorry, 15 minutes, about 5 questions. So yeah, about 5 questions. Yeah. Okay, other questions? Again, if you have more questions about the quiz won't start until after class on Thursday. Okay, so we ended up going through some of the reactions. One of the things I didn't show you last time that I meant to when I was going back through my notes is that we were looking at fuming sulfuric acid, right? But we also said that if you take concentrated sulfuric acid, that you can get the reaction. So the question, you know, you can think about is how do we get to the SO3 as our intermediate? So let's take a look at that one. So if you have concentrated sulfuric acid, what you're going to have in the solution is you're going to have lots of the sulfuric acid, right? So what happens is we can get a protonation we get the protonated sulfonate sulfuric acid. And we can think about that just leaving by itself. But this is a hypervalent sulfur. So it's also plausible to think about this occurring all in one step instead of two steps. What that does is give us now this species, right, which is close to that SO3 that we used for the sulfonation of an aromatic. And if we have some base, and again, here, anything is going to be a good base. So even the sulfonate could be a base here. So we get the proton abstraction, right? And that gives us our, so in concentrated, hot concentrated sulfuric acid, I can create that SO3 group that we use for the aromatic sulfonation. So again, if we take this, right, that react here. Right, we end up with a carbocation, right, that rearranges, but then the next step is going to be deprotonation, and we can take a base. And again, because this acid is so, this proton wants to leave to reform the aromaticity, anything that can accept that proton will act as the base here. So that's why you'll see that I don't usually specify one. Anything here that's strong enough to, anything will really pull off that proton. That reforms my aromaticity. And then the last step is just to get that proton back onto the sulfonate. All right, so we have electrophilic addition, right? We get the acid base, we get the proton transfer. That completes the electrophilic aromatic substitution. Okay. Questions about this one? Okay. So I just wanted to show you how we make that SO3 if it's not already added. So fuming sulfuric acid has SO3 in it. If you take concentrated sulfuric acid and heat it up, you will create SO3 through this process. Okay, nitration. Again, we're going through several aromatic electrophilic substitution reactions. So if we take nitric acid in sulfuric acid, we can nitrate aromatics. So get the NO2. Again, this is an aromatic electrophilic substitution, but the first thing we need to do is activate our nitric acid. So the nitric acid by itself, unless it's fuming nitric acid, won't work. So usually fuming nitric acid is also incredibly explosive, so you don't see that. Fuming sulfuric acid is incredibly corrosive, but corrosive is slightly better than explosive. So, what we choose to use is nitric acid and sulfuric acid. What happens in those is very similar to sulfuric acid. That's the reason I wanted to go back and look at that one. So the HNO3 is this compound. We react that with sulfuric acid. Okay, so the nitric acid actually gets protonated by the sulfuric acid. And then at this point, we get loss of the water. So lone pair come in, take off the water. And that will give us the NO2 plus. And actually that should have been a plus there. And that should have been a plus there. So the nitrogen should have had a plus all the way through. Here we lose the water. Right, so then that becomes our electrophilic group. So like with the sulfuric acid, they react together to give us the SO3. Here, the nitric acid reacts with the sulfuric acid to give us NO2. Then the NO2 can react with aromatic. I see people trying to finish up. So nitric acid, lone pair picks up the proton, electrons go back. So that gives us our byproduct. Then the next lone pair on the oxygen that's negative comes back, kicks off water, expelling water, giving us the nitronium ion, this NO2 plus. That then reacts with my aromatic. Okay. So my aromatic group, we've got our alkene, nucleophile attacks that electrophile, electrons go down to the oxygen. And then here again, we've broken up the aromaticity. So we need a base to pick up that proton. So we do a proton transfer. Recreate that aromatic system. That's the driving force, right? And then we have our nitro group on the side. And I keep dropping the positive on my nitrogen. Questions about this one? Okay. Once, I guess it's not really an alarm. So nitro. So the nitro groups, we'll see that they have some usage. In material science, particularly as we get into directing groups, we'll see that they created one of the Nobel Prizes, actually funded the Nobel Prize. But in the one of the things that nitro groups are good for is that you can then reduce the nitro group. So you can add the group there and then reduce it. And of course, that reduction of the nitro, it gets us to a biologically important entity, which is the amine. So if we nitrate an aromatic, we can then reduce that aromatic in the presence of iron and acid or zinc and acid, followed by a mild base. To give us the amine. So we start with the nitro, we end up with the amine. Then we can use iron or zinc for this. The first step, since we're an acid, here I'm just going to change it to zinc, so you'll see both versions. That gets us to the ammonium. So the first step, and we're not going to go through the mechanism on this one, gets us to the ammonium, which is just the protonated amine. And then when we add our base, well, the second step is just removing that proton to get us to the free base or the amine. And of course, aromatic amines are common in biological systems. So you'll see those in several places in base pairs, different types of structure, you'll see these. So the nitro is actually a one way to get to the amine. Nitros by themselves have material properties, but for this type of class with lots of health professionals, the reason that you would want to make the nitro is then to reduce it down to the amine. And the amines have biologically active components there. So you can use iron or zinc and acid followed by base. You can also do this with a mild hydrogen reduction. And again, remember that the aromatic won't reduce under normal atmospheric temperature and pressure. So I can reduce the nitro group to the amine with hydrogen and palladium. Okay. Now I have to watch if there's other groups on there, but the aromatic by itself will not be reduced with just hydrogen and palladium or hydrogen and platinum. Now, hydrogen nickel at 150 degrees and 100 atmospheres will reduce the aromatic, but not at room temperature and room atmosphere. So 1 atmosphere and 25 degrees isn't going to reduce the aromatic. Okay. Questions about this one? Okay. Let's do one more and then we'll do a try this. Okay, Friedel class alkylation. Again, aromatic electrophilic substitution. What this one does is adds an alkyl group to the benzene. Okay. The important thing to remember here is I've made a carbon-carbon bond. Carbon-carbon bonds means I've changed the carbon skeleton. Anytime you see a carbon-carbon bond making or bond breaking, you should make special note of that. Lots of the things we do are functional group changes. Adding a sulfonate to a benzoic acid does not change the structure, it just changes its functional group, right? What this does is changes my carbon skeleton, right? So watch for carbon skeleton changes. And so for the alkylation, one of the things that this is important for is the fact that it makes carbon-carbon bonds. The first thing that happens is the chloride reacts with the AlCl3. Remember aluminum chloride, if we put all of our lone pairs in here, remember that aluminum has an empty orbital. So aluminum and boron are fine with 3 bonds, right? And an empty p orbital. So this is an empty p orbital. That empty p orbital can accept electrons. There is a close affinity between aluminum and chlorine. Okay, so we get loss of the electrons here, which forms the carbocation. So this is a high energy reaction. We're going through a full carbocation. You can think that secondary carbocations are going to react well. Primary carbocations are probably not going to react at all. And that's true. Primary alcohol carbocations are very difficult, although they do occur. Now, once we have the carbocation, then we have our electrophilic aromatic substitution. So same reaction. Third verse, or by this time, fifth verse, right? So nucleophile attacks the carbocation, the electrophile. That gives me this tetrahedral intermediate. Okay. So I've got the carbocation here. That proton, it wants to reform the aromaticity. So base, and even though AlCl4 minus is not a good base, it is in this case, right? So that's a very acidic proton because it wants to go back to aromaticity. So I reform that aromatic. Okay, new electrophile, same mechanism. And I form the substitution. Okay, questions about this one? Now, there are several issues with this one. So Friedel-Crafts alkylation has some potential issues. Okay. Issue 1 is rearrangement. Okay. What we're trying to do here, right, is add an alkyl group by going through a carbocation. So therefore, anytime we go through a carbocation, what can happen? We get carbocation rearrangements, right? So we have carbocation rearrangements that are possible here. So if I wanted to take this benzene and react it with this chloride, and again, primaries aren't favored, but they can occur. But what's going to happen is that I only get one product out of this. And that product is not the terminal, that product is the secondary, right? So I don't get the primary, I get the secondary. What I had wanted to do was make this, right? But I don't get any of that. The reason is that once I form this carbocation, that primary carbocation, right, I'm going to get a rearrangement. And I learned to put squiggly lines, but all that means is I'm moving that bond. And by that moving that bond, what I've done is I put the carbocation at the second. So therefore, this is the reactive carbocation. So the first thing we have to watch out for is rearrangement. So making a primary group like this is something we can't do with a Friedel-Crafts acylation, right? It's always going to rearrange to go to at least a secondary, if not tertiary carbocation. The second issue with this, and it's not really an issue, it's just something you must be aware of, is that this doesn't work with sp2 carbons. The reason for this is that sp2 carbocation is not stable, right? So if I try this AlCl3, I get no reaction. Because to do that, I would have had to form this carbocation, right? And this is a very unstable carbocation, that sp2 carbocation, not an allylic, right? Not benzylic, but the actual carbocation on the sp2 carbon is unstable. So that's why I get no reaction. The other one that you'll see is sp2 when the chloride is on the aromatic like this, right? That's still an sp2 carbon. And that gives no reaction. So I can't use this Friedel-Crafts alkylation to make a bond between two aromatics or a bond between a vinylic, a sp2 carbon double bond. And now, could I do it with allylic? Yes, but that's not an sp2 carbon, that's an sp3 carbon. One other potential problem, and you have this, you have this potential problem, and it doesn't usually make a big difference, but it does in a few cases. And that's if I add, like, say this something that's really easy to make a carbocation, like this tertiary. I can end up with di alkylation, right? So the first step would be to create this group, right, to get the mono, but then that can go here. And the reason is that that group there, and we're going to look at this maybe at the end of the class today. If not today, we'll look at it on Thursday. This is an activating group. Okay. Why would that be an activating group? Well, think about the way this reacts. This reacts by going through a carbocation, right? That's not right. Ugh. Don't worry. Oh, we'll draw it again. Okay. So if we think about this intermediate, right, adding that second one, what have we done now by having that alkyl group there? Can that alkyl group stabilize? Can this alkyl group stabilize that carbocation? Yes, right? So therefore, if I can stabilize the carbocation intermediate in an electrophilic aromatic substitution, what does that do to the energy of activation? If I stabilize the carbocation, that lowers the energy of activation, right? So what does that mean as far as the speed of the reaction? Speed of reaction goes faster, right? So I've stabilized that carbocation. So anything that can stabilize that carbocation is going to be a activating group, right? So since that's an activating group, that means that this molecule reacts faster than this molecule, right? So I've added a group to it that makes it react faster. And if the carbocation is easy to make, I can end up with multiple groups. Okay, the fourth issue with Friedel-Crafts alkylation is deactivating groups. If we have something that destabilizes the ring, like say a nitro group, which is pulling the electron density away from the ring, and I try to do Friedel-Crafts acylation with this, I get no reaction. The deactivating groups that'll stop this are the nitro, right? The sulfonate, and carbonyls. So if I have a strongly deactivating group, then I can't do the Friedel-Crafts acylation, alkylation, Friedel-Crafts alkylation. Okay, so let's go back and look at this. So first one is we're always going to end up with rearrangements because we're going through a carbocation. So therefore, there's some side groups that we just can't attach by Friedel-Crafts alkylation. We can't add sp2 carbons because sp2 carbons won't create the carbocation. So therefore, that will not work. Third one is we potentially get multiple alkylations. That's usually not a big issue, but it is something to watch for. And if you're worried about that, there may be a better way to do it. And then the last one is it doesn't work for some groups that are attached to the ring. So if I have a nitrobenzene, then I can't do Friedel-Crafts alkylation, right? If I do sulfonates, I can't do Friedel-Crafts alkylation, okay? Y'all look like you're glazed over, so let's try some and then we will move on. So let's try some of these. Okay, so let's take a little while. Let's try these. Feel free to talk to your neighbor. Okay, let's go ahead and take a look. So on the first one, okay, we're adding a bromine, right? So we're going to need Br2. Oh, if I put the R in there, Br2, right? Is that sufficient? Not for the aromatic, right? So then I'm going to need, I could put iron, or I could put FeBr3. So Br2 over iron would work as well. AlCl3 wouldn't work. That's what you use for chlorine, and you don't want to mix your halides, right? You wouldn't want bromide ions and halide chloride ions in the same thing. So either of these work fine. Okay, questions about that one? Okay, on the next one we have NO2, so we're going to want HNO3. Is that sufficient? No, we need our activator, and our activator in this case is sulfuric acid, right? And that's going to give us a product. Sometimes you'll see heat on these. Heat's not always necessary, but of course, if you heat anything up, it goes faster. Okay. Any questions about this one? Some texts will also have HNO3 fuming. And like I said, older textbooks will have that. Textbooks with authors that started in the 70s will have that, but really it's hard to buy fuming nitric acid because it's a dangerous compound. Okay, the last one, let me give you the answer and then we might need to go take a look at it. Okay. On this one, we get the tertiary group, right? What happens is with the AlCl3 and the chloride, we end up forming this carbocation, right? But that's a secondary carbocation next to a tertiary group. So then that rearranges to give me this carbocation. That's the most stable carbocation, and then that carbocation is the one that reacts with the aromatic. So you get a rearrangement to form the most stable carbocation. That most stable carbocation right is the one that adds. So in this case, we end up with this. And then of course the proton transfer at the end to reform the aromaticity. So base pulls that proton off, giving the electrons back to the ring. That allows it to reform my aromatic. Okay, questions about this one? So we saw there were several problems with the Friedel-Crafts alkylation. So that led to the development of Friedel-Crafts acylation. And so for Friedel-Crafts acylation, it's very similar, except instead of an alkyl halide, I'm going to use an acid chloride. Okay. And instead of adding just an alkane, AlCl3, right, what I'm going to do is add the carbonyl. Okay, there's some advantages to this. First, there's no rearrangement. And we'll see why in a second. We can potentially add carbonyls that are linear. In fact, they're going to be linear, right? Because the carbonyl already has double bond to oxygen. So I'm not going to have any tertiary or secondary groups coming right off. And the carbonyl is a deactivator. And we'll get into a long discussion of deactivating groups. But the reason for that is that we have this positive right outside the ring, right? That pulls a lot of electron density. So the carbonyl is deactivator. Why is it important that the carbonyl is deactivator? Are we going to get more than one addition? No, right? So the Friedel-Crafts acylation takes care of a few of the things that Friedel-Crafts alkylation had. Rearrangements, there are no rearrangements. That you can add a linear group. You couldn't do that with the alkylation, and then we don't have to worry about getting a lot of multiple reactions. The way this works is similarly, right? We could bring in our Lewis acid, react that. So our lone pair here reacts with that group. That gives us the attached. Then there's a couple of ways to think about it. I'm going to show you the way where the electrons come down. So these electrons come down, kick that off. That results in this oscillium ion. Right, and then the AlCl4 minus. This is oscillium ion. Right, we can draw it this way, but it also has a resonance structure. We take these electrons. Oh, wrong charge. Make sure you correct this. There should be a positive there. And then positive there. So my oscillium ion is these two. This is why there's no rearrangements, right? Because the lone pair from the oxygen can come down, stabilize that carbon positive, right? And then I can get that delocalizing back to give the carbon positive. So I go back and forth between these two, right? You'll see me use this one quite a bit because if we think about these two, this one has an empty orbital. This one does not have an empty orbital. So which one's more stable? This is the more stable ion of the resonance contributors, right? This one shows you where the most reactive spot is. This one shows you that you have all full octet, okay? Because of this oscillium, we have no rearrangement, right? So we have a way to create this. We're not going to have any changes in our carbon skeleton. We're just going to have that carbonyl. So once we form that, then our aromatic will react with that through an electrophilic aromatic substitution. So we've learned 7, 8 reactions, but only one mechanism, right? All the mechanisms are electrophilic aromatic substitution. So nucleophile attacks, oops, a little off there. Nucleophile attacks electrophile, leaving group is the pi bond. That gives us the tetrahedral intermediate with the hydrogen. Our carbonyl, right, the carbocation here. Carbocation is delocalized. And then our base, and again, the AlCl3 could act as a base because this proton wants to leave, because when it leaves, it reforms that carbocation. So if I wanted to go from here to here, right? I could do that by going through the Friedel-Crafts acylation, right? That'll get me to this point. Then the question is, can I get here? if I had tried this with the Friedel-Crafts alkylation, right, my product would have been this one, right? So I can't do it through Friedel-Crafts alkylation. I won't get to that product, but I could do it in Friedel-Crafts acylation if I could reduce that carbonyl. There's a couple of ways you can reduce that carbonyl. The book focuses on one right now, and since it's focusing on one, we'll focus on one, and that's the Clemmensen reduction. So in the Clemmensen reduction, I use zinc amalgam. That's just a fancy way to say zinc and mercury, acid, and some heat. That will reduce that benzylic carbonyl down to the alkane. We're not going to go through the mechanism on this one. So in our example above, we could have taken this Friedel-Crafts acylation to give us this long chain addition. And then we could have used the zinc and amalgam. This is a new reaction to give us the primary addition. Okay. So where Friedel-Crafts alkylation won't work to give us just a simple side chain, Friedel-Crafts acylation can. Now we don't have to do that with all of them. We might want to leave the carbonyl. We might want to reduce the carbonyl to an alcohol, right? As we get into carbonyl reactions, there's even other things we could do. But one way to make the basic carbon structures like these is to go through the acylation and then do the Clemmensen reduction. Before we change gears, let's try this. All right, let's propose the synthesis, the reagents for these two syntheses. Again, take a little time to work by yourself and then feel free to have a conversation with your neighbor. All right, let's go ahead and take a look. In the first one, okay, we have a benzene and we're adding 1, 2, 3, 4, 5 carbons. Okay, it's important to know what the 5 carbons are all going to be at a primary position. Would this be possible with the alkylation? If we had tried to use the alkylation, we would have ended up with attachment at a secondary position. Okay? So therefore, that's going to point me towards the acylation. So first step is going to be the carbonyl with 5 carbons, 1, 2, 3, 4, 5, and then the AlCl3, right? That's going to give me the carbon structure, right? And then what I need in the second step is the reduction of the carbonyl. So second step is going to be the zinc and mercury, right? Oops, just one zinc and mercury. And then HCl and some heat. Okay. So a Clemmensen reduction. In the second one, okay, questions about the first one? Okay. In the second one, could I do alkylation? Plausibly here, right? Because if I look at it, I could have started with this and AlCl3, and what that would have given me would have been this carbocation, which is stabilized by delocalization. So here, although it's not a phenylic, right, it's an allylic, right? So having the chloride not on an sp2 but next to an sp2 is allowed, and because both of these are identical, right, this would give me a nice clean synthesis. It's an easy to form carbonyl, which is, a carbocation, which is useful for Friedel-Crafts alkylation, right? And because it's symmetric, I don't have to worry about getting 2 different products. So this allylic chloride with AlCl3 would give me this product in high yield. Questions about the Friedel-Crafts alkylation and acylation? So lots of different reactions to learn, okay? So one of the things I would suggest, if you did not do this in Organic 1, I would do it now, is make some flashcards and make the flashcards questions. Okay, on the front, ask yourself what the reaction products are. So what is the product? On the back, ask another question. What reactants do you need to make nitrobenzene? And hopefully your handwriting is better than mine. Most people make flashcards with information. Information is not the way that your brain tries to learn things. It tries to learn things by recall. So you want to make your flashcards not informational flashcards, make them questions, right? So set them up with a question. So when you look at them, it's like, okay, what's the reagent I need? Then on the backside, you put what the reagent is, but you're asking yourself a separate question. So now you have a question. Now you have flashcards that provide the answer on the back, but also you can turn those flashcards around and you can study that material in a different way, right? Because the way you're going to get the questions on these are going to be either provide the reagents or provide the products. Every once in a while, you'll have provide the starting material, right? But most of them are going to be this way. If you set up your flashcards this way, you're going to be doing what brain science says we should be doing, which is causing recall, right? Causing recall. If you have a study partner, read these out to each other almost every time y'all get together to study, okay? I would make these and don't buy them, right? Why make them? It actually turns out that if I type my notes, that typing my notes is not as productive as using my hand. Now, one of the reasons for that is it actually takes less muscle memory to type than it does to write. So if you're taking notes by hand, even if it's on an electronic device, you'll remember those notes better than if you're typing notes in class. If you're typing in notes in class, you're more or less automatically going through the brain without really learning it. And so there actually is an advantage to use this. If you are buying your flashcards, a lot of the learning that came in to that is missed, right? Because you did not make your own flashcards, right? So make your own flashcards, start making them. You got a bunch to make over the next few days to get ready for the exam next week, okay? So one of the questions I keep getting is how to study for it. One of the ways to study for it is to make these flashcards. You want some of these basic things. If I was going to ask you how you turn benzene into nitrobenzene, you should get to the point where that's quick, right? Nitric acid, sulfuric acid. The other thing I would say is that if you are a verbal learner, right, make a note here that this is benzene with nitric acid and sulfuric acid, right? And read yourself that sentence. All of these reactions can be turned into a sentence. So if you're more a verbal versus a visual learner, turn everything into a sentence. If you're an auditory learner, then have somebody read the questions to you and you read out the answers, okay? Now, anybody can slip back and forth. They used to have this kind of, this is your learning style and you're stuck there. Turns out that's bogus, but there's still people that have a preference over one or the other. And if you are, and most of the people that end up in college are really good verbal learners, then what you want to do is you want to put things in a verbal phrase, even if it's, so even if you're thinking about human anatomy, what you want to think about is this bone is attached to that bone, is attached to that bone, and sing a little song about it. You could do the same thing with organs, right? So do that for these, okay. All right, we got some time left, so I do want to go ahead and don't want to waste too much time. So let's go ahead and move into activation and deactivation. So far we've been doing all our reactions with just benzene. Now let's look at substituents, right? So what happens when we try to reaction with a substituent? So let's start with the alkyl group. So let's take toluene, right, and react that with nitric acid and sulfuric acid. And we have three possible products. We can have the orthonitro, right? So the orthonitro toluene. We could have the meta-nitro toluene, or we could have the paranitro. If you look really hard, you'll find all three of these, and the ratios of these are about 63%, 7%, and about 30%. Now there's a little bit of statistics in this as well. How many ortho positions do I have? I have 2 ortho positions, right? I have 2 meta positions. And then how many para positions do I have? 1. So therefore, if we look at this, what is really the difference between our ortho, right, our meta, and or our para or meta and our ortho? Well, the meta, right, is very, very low. Even though we have 2 of these, it's pretty low. But then if we look at our para to the ortho, is there a big favoritism of ortho over para? Well, it looks like 63 to 30. Well, shoot, yeah, that's big. But really, what is it? It's 31.5 to 30, right? So we have twice the opportunity to substitute an ortho than we do para. So we have a slight advantage of the ortho over the para. So therefore, when we look at this methyl group, right, The methyl group seems to be directing to which two groups? Ortho and para. So the activating and deactivating is also going to come with a directing, right? Now, to understand whether something is activating or deactivating, we need to look and see what's happening to the mechanism. To understand whether something is directing, we need to look at what are the products. And from that, we'll be able to stipulate back to the mechanism and show why that is the case, right? So the question here is, why is ortho and para favored over meta? So let's look at the mechanism, right? So we're going to have the methyl, and if we attach the nitro to this position, right, I'll get this, and this would give me several possible carbocations, right? I've got this one with the nitro and the hydrogen, but I'd also have this one with the carbocation here. And because of hyperconjugation, right? And I shouldn't show it with a plus, it's not dipole, it's hyperconjugation. I can help stabilize that carbocation, right? So the methyl, right, stabilizes carbocation. Right, so that's the ortho. So if we had added the nitro to the ortho, that's the result. If we then look at the meta, so now we're adding the nitro to the meta. Then when I show my delocalization, I can get it here, right, in the ortho position to the methyl, and I potentially could get it to the para position. But what do you notice about the meta addition? Is it ever near the CH3? No. So therefore, in the first one, right, I'm stabilizing it. Right? I'm stabilizing that carbocation. In the second one, am I stabilizing it? No. Am I destabilizing it? No. I'm just not stabilizing it. Okay. That's going to be important on Thursday when we get to deactivation. If we then look at the para, so now we're going to say, what if we had added the nitro to the para? Okay. We get the positive, and we have the resonance contributors. And that's pretty ugly. So let's draw that over again. So we get that carbocation. And then one more delocalization. And here we see, right, that we have stabilization of that alkene. So the ortho and para additions, right, give me a carbocation that can be stabilized by my alkyl group. The meta does not. When I stabilize something, that's activation. Because if I can stabilize a carbocation, what does that mean for my energy of activation? That brings the energy of activation down. If the energy of activation goes down, right, the reaction goes faster. So I've activated the reaction, right? The ortho and the para here becomes, from the ortho will allow me to get the carbocation in the right place. And the para position, the bottom position, will allow me to get the carbocation in the right place. But the meta position, right, does not allow that. So with the alkyl groups are activating and ortho and para directing, okay? Activating and ortho para directing because it destabilizes or stabilizes? Because it stabilizes. That's going to be important, right? So if we look at this, would a meta addition be slower? No. Would it be as fast as an ortho and para? No, right? So the ortho and para become faster. The meta has no real advantage, so therefore the one with the advantage wins, okay? And that's